maximal torus. The algebra G, T, the algebra, and we also had the notation XT, which is the group of characters written additively, though the actual thing is multiplication of characters. The group of characters which is isomorphic, Z, and are denoted by FT, regular functions. Which is anything else. And so each character is C alpha X. And in fact, this can be identified in the group algebra with its multiplication and that into the group algebra of on T on XT, which as I said is not. So it's really group algebra over C. Algebra C value functions. So,
I think the mic is not turned on.
thought I turned it on.
The mic is on.
In any case, I thought also my voice also is loud enough. I thought. Group algebra, FT is same as the group algebra. W acts on T. W is the normalizer T modulo T. It's a finite group and has a set of generators, elements W alpha and delta. W alpha for alpha and phi. W alpha is the reflection with respect to hyperplane. When you treat it as an automorphism of P or TC or H. The reflection means something which leaves invariant hyperplane and acts as x going to minus x on its orthogonal component. So the group W is generated by this. And once you have this definition, we also have subspaces of FT which are denoted FTW, which is invariance under W, functions F in FT, W of F equals F. The group operates on functions, so this makes sense. And they also introduce T W alternating, which is F in FT, WF equals epsilon W, epsilon being the homomorphism of W into plus minus. Calling the signature, the special case of W is the permutation group and its usual signature of that. Epsilon is the usual signature. Okay, this is all the notation I introduced. Now what I'm going to tell you is what is the classification of finite dimensional representations of compact groups. We know that every representation is not completely reducible, so it's a directional irreducible representations. So to understand all representations, we need to know what are all the irreducible representations. And let me observe, when you take a finite dimensional representation, V is a finite dimensional representation of G. So G goes to on a complex vector space. If I call it rho, we know that V breaks up into a direct sum of eigenspaces for T. V is sigma V lambda, lambda in the character group, some finite subset of character group. Is how it decomposes. We know that the torus is abelian, and you decompose V with respect to the torus. It has to break into irreducible one-dimensional representations. Each one-dimensional representation is an eigenspace for a suitable character, where V lambda equals V we call it rho T V equals lambda T. As I have been doing, always consider xt as a subspace of home HR. Every character induces a homomorphism of the corresponding Lie algebra TC, Lie algebra T, and therefore of TC into C. And that, when you restrict to H, goes into R, is what we have seen already. So xt is to be considered as a subset of OHR. So each character is a linear form on the space H. We have also seen, the character, each character defines a linear form, and when you look at the Lie algebra, you don't notice the representation of GC induced by rho the angular G is a direct sum. Once again, I'll write it as not G. We don't know some decomposition V lambda, and it's a set of eigencharacters which also can thought of as linear forms, and we know that lambda of H is in R. We've seen all this. So, and we've seen that if the group is simply connected, representations of G is same as representations of the Lie algebra. And therefore, so we are looking at complex representation, so finite dimensional representation. So finite representation G is same as finite representations of the Lie algebra or complex numbers GC, which are finite dimensional. That follows. I mean, there's a little bit to be worried about, because starting the representation of GC, it gives the representation of the compact group. You have to use that fact to conclude the eigenvalues are in R. For H, the eigenvalues are, to conclude that for an arbitrary representation, you have to go to refer to the compact group as well. But you don't have to have a compact group. Still, this statement is true. That is because there is always a compact form, as they say. Any G is automatically the complexification of a suitable Lie algebra of a suitable compact. Okay. So what we want to classify in the problem that we classify finite dimensional irreducible representations. So now we know that if such a representation we just now saying breaks up into V lambda, a finite set subset of H star, which is home HR. On this, we have introduced an order, a total order. So we can talk of the highest of these lambda. I recall we call the lambda in S are the weights of rho. So given any representation, there is going to be a highest weight of that representation. So let lambda rho be the highest maximum of lambda in S. This is called the highest weight of rho. Okay, then with this notation, I can state the theorem which classifies independent representations. But one more definition before that. The weight lambda on H is dominant integral. Yeah. Dominant if it's dominant if lambda alpha is greater than or equal to 0 for every positive alpha, which is equal to saying for every simple alpha. But I should probably write H alpha. Lambda H alpha is greater than 0 because we want an element in the real algebra H. If for every positive alpha, if lambda H alpha is greater than 0, then it is dominant. Obviously, it's true for simple, it's true for every possible root, because every possible root is a linear combination of positive, non-negative integral coefficients of simple roots. So, this is the definition of dominant. It's lambda H alpha is greater than 0 for every simple alpha. Also, we'll say that lambda is integral if the following thing happens. If 2 lambda H alpha divided by, this is the linear form operator, but you also seen that this gives you a linear product on the real algebra itself, so we can talk of this. Look at this ratio. This is on the killing form is positive definite on H. We have seen that. So this is always non-zero if H alpha is non-zero, and if alpha is non-zero, H alpha is non-zero. Is integral if this is in Z. And then with this notions and definition, I can state the theorem. See, this integrality is really equal to saying that the representation integrates to T. The linear form integrates to a character on T. That's what it means. If you have a linear form of the linear algebra, it doesn't always give you a homomorphism with corresponding group. Here, in this case, if you have a representative big linear algebra, the sensitive algebra, of course it integrates. And then if you restrict to T, you get a representation of T, which is the integral of a representation, the corresponding representation is its linear algebra. But it's so the given representation gives a representation of algebra, and then you want to integrate it to T, you need a condition. No, the exponential map from the Lie algebra to the Lie group, in the abelian case, it's a torus, is not injected. It is a kernel which is a lattice, which is a Z modulo maximal rank. So the condition that this is 2 lambda H alpha by H alpha H alpha is in Z is equivalent to the fact that the representation defined in the linear form at the Lie algebra level integrates the representation in the compact group T. So that is the This is that condition. So I'm sorry, I should have said from the beginning G is simply connected. In the last lecture I said this time I didn't say it. G is a compact simply connected group. Otherwise, really don't integrate two.
Then I think one week for more condition.
Sorry?
Then I think there is one more condition called analytically integral.
Canonical?
Analytically integral.
Sorry.
Analytically integral.
And what do you mean by analytical? Everything is analytic in the finite dimensional case. There is no problem. In the finite dimensional case, there is no. In fact, no. In a book like Chevalier's unique group is an analytic group, analytic manifold. Maybe some other books talk of them as C-infinity manifolds. But analytic manifolds is in the Chevalier's book, that's a definition, and Chevalier is my Bible. In any case, that definition is what will work for periodic D groups. You can't talk of C-infinity in the periodic category at all. It just doesn't make any sense practically. Okay, the theorem is the following. For every, let rho be a finite dimensional representation. And lambda rho is highest weight. Then lambda rho is dominant integral. That is, integral is essentially the fact that the characters, this linear form lambda rho integrates to a character on the doors. So that's the condition of integrality. So that's certainly easy to see. But that lambda rho is dominant integral requires a little bit of proof. We'll see that. Conversely, given a dominant integral linear form element in a star, there is a unique irreducible representation dominant element lambda in a star. There is a unique irreducible representation, finite dimensional, irreducible representation with lambda equal to lambda rho, the dominant weight of unique irreducible representation rho, dominant weight lambda. Dominant weight of. So that's the theorem. So any it starts with an irreducible representation. Of course, it has a dominant weight. That's obvious. It's not obvious it's dominant. You get the highest weight. The highest weight is automatically dominant in the integral. Conversely, given a dominant integral element, linear form lambda and x star, there is a unique finite dimensional irreducible representation rho with lambda equal to lambda rho. The highest weight equal to lambda. In other words, there is a bijective correspondence between irreducible finite dimensional representation, or rather their equivalence classes, with the set of dominant weights. Once you have that, you can ask, so I am given a dominant weight, I get an irreducible representation, what is its character? As a character is a function on G, but it's we have already seen if you restrict to T, you know the character on the whole of G because everything is a conjugate in T. So what is the character representation on T in terms of lambda rho is the, and that is what the character formula N1Y is all about. Right. It's row already. Okay. But I have to. So once I have the dominant this statement, I can ask whether I can express the character in terms of lambda row. So yes, indeed you can, and this is the theorem of weight which I'll state. So the character, the wild character formula as I call it, says the following. Let lambda rho be the dominant weight, O, the highest weight, is automatically dominant. A representation may have more than one dominant weight. It's possible. In it, among the weights, there can be two which are dominant or even more which are dominant. But the highest weight is certainly dominant. Let lambda be the highest weight of G. Let this is by what I was let me write R be the weight sigma half sigma half the sum of the positive roots. Then this is an aside if you like. 2R alpha by alpha alpha or x alpha x alpha 2R alpha by alpha alpha equals 1 for every alpha delta. It's a very special dominant weight. It takes the value 1 on every simple root. Alpha, the list of simple roots. That I call R. With this notation, the theorem is chi rho, which is character of rho, is given by the following formula. Chi rho of T is the torus, equals sigma 2 in W 2 of epsilon sigma epsilon 2 of lambda plus rho divided by sigma 2 in W epsilon 2 of rho epsilon 2 times W tau. This is the formula. So if you know the dominant highest weight, you know the character completely. Now let me make number of points. See here, essentially what you are doing is averaging lambda plus rho with the weight, the weighted average over the wild group. The weight is epsilon 2. So this
That totally rho, not lambda plus lambda plus gamma.
lambda plus
No, I think you have
not rho, sorry.
R.
R. The problem is rho is usual notation. Since I am using representation rho for representation, I am introducing R. Here also it should be epsilon 2 R. So I form the alternating sums like this. I am averaging with epsilon 2 there. So this both numerator and denominator belong to what I call FTW alternating. A. So the ratio is symmetric. When you apply the element to the wild group, this will change to minus of the same thing. If the element of the while group, a signature minus 1. If signature is 1, it will go into the same element. Same thing is true below. So when you take the ratio, it will be symmetric. Sorry?
What will exponent?
Formula?
Exponents. I mean, it should be.
Hold on, I am identifying characters of the group as a subset of linear forms. So I'll allow myself to confuse linear forms of the linear algebra with characters of the torus, provided they are characters of the torus. So this ratio is invariant under the while group. It belongs to sorry about this notation. It belongs to FTW. No alternation. Which is what the character should be. The character is invariant under the while group. So when you take the ratio, it becomes invariant under the while group. So that is the theorem. Okay, I am going to say something about this. I won't give the full proof, and I will then go on to sketch a proof of that. Even that I may have to wave hands a little bit. I don't think I need to, but we'll see. Okay. How do I prove this theorem? Well, let's look at the represented row GC on the vector space on endomorph system. Then if you look, it breaks up into sigma v lambda or some weights lambda and s, and observe that if you take x in g alpha and v in v lambda, xv will fall into g alpha plus lambda. That is, if you take something in the eigenspace of lambda in the group, in the vector space, and something in the eigenspace of alpha in the linear algebra, xv will fall to g alpha plus lambda. Into the eigenspace corresponds to alpha plus lambda, which could be 0, because if you keep on applying alpha several times, you get an infinite sequence of, so the space is finite dimension. So this is g alpha plus lambda. I've been writing gc alpha plus lambda. Oh, vc alpha. Vc plus alpha plus lambda. If what I want to say is this: vc alpha. I don't write. Sorry, I've been writing v lambda, right? V alpha plus lambda. It is understood that v alpha plus lambda is 0 if alpha plus lambda is not an eigenlinear form for H. I have been calling them eigenspaces. Eigenspaces will correspond only to eigenlinear forms. So if the eigenlinear form is 0, I say the corresponding eigenspace is 0. I mean, the corresponding eigenspace is 0. If there's no, sorry, if alpha plus lambda is not an eigenlinear form, define alpha plus lambda is not an eigenspace, you know. This is the easy exercise. I'm going to leave you to check that. The upshot is, if you look at g alpha, rho g alpha on v lambda, W, take the highest weight for alpha in positive groups. To take the highest weight, apply g alpha, it falls into v lambda plus alpha, but lambda plus alpha is not a weight, it's bigger than lambda, and therefore it's sorry, whatever the rho should be. So this falls into, this is contained in v lambda rho plus alpha. But lambda rho is the highest weight. So lambda rho plus alpha is not a weight of the representation. It's not an eigenspace, so it has to be 0. So what happens is you pick a vector v0 in v lambda rho. What happens is all of g alpha, all the g alpha is annihilated. Pick one. v0 is 0 for every alpha in phi plus. Now, this means let me denote by n plus the sum of the g alphas in phi plus. Observe, have here again gc alpha bracket with gc beta falls into gc alpha plus beta if alpha plus beta are all roots. Sometimes alpha plus beta could be 0, in which case it falls into the torus, linear algebra of the torus. If beta is minus alpha, but anyway, if you look at alpha beta happens to be roots, this is true. This is true if alpha plus beta is not 0. This alpha plus beta may not be root. If it's not a root, this becomes 0. That would mean g alpha and g beta commute. If alpha plus beta is not a root, g alpha and g beta commute. That's what happens then. Okay, you have this bracket operation. This implies, in particular, that n plus is an nilpotent Lie algebra. What happens is this: take this entire thing and take bracket with itself. What happens? Every g alpha that occurs in the bracket after the bracket operation is sum of two roots, sum of two positive roots. Do it again from bracket, then it becomes sum of 3 roots and so on. So the whole chain, this descending central series has to finally terminate. So it's a nilpotent Lie algebra. And this statement also shows that n plus acts as an algebra of nilpotent endomorphisms on V. Why? Start with any one eigenspace, any one weight space, keep applying it. The weight, if you apply keeping up, and plus you go to higher and higher weight, ultimately it has to go to 0 because the thing has to terminate. It's a finite dimensional space, it has to terminate. So it acts as, in fact, if you choose a basis compatible with the eigenspace, the weight space decomposition, everything becomes upper triangular. All the endomorphisms coming from n plus become upper triangular. If you choose a basis which is compatible, choose a basis which is compatible with the, and in the same order as the order of the weights. V lambda may be of a higher dimension. Within V lambda, you don't care how you choose the basis, choose whichever way you want. So this actually n plus becomes rho of n plus is upper triangular with respect to suitable basis. Upper triangular with 0 on the diagonal. So it becomes, and let me also denote by B a subspace T plus n plus H plus n plus. All these are now complex subspaces. I call this B. B is, it stands for Borel. There is a paper of Borel and Tate's called Group with the Thief. At one point is the footnote. They have just defined the Borel subgroup. The footnote says, against the protests of one of the author, we have decided to give this name to this group. A little later, at some other point, again a footnote. Again, despite the protests of the second author, we decided to call this stitch system. Anyway, that paper is really public service. The proofs are not very. Anybody with some expertise can push the proofs, but nobody would have bothered to write it down. It's typical of Borel that he wants to do this kind of service. Anyway, of course, the crucial point is they realized that if you want to handle the algebras on arbitrary fields, the right object to first pitch on is the so-called split torus. The torus which is diagonalizable over the field. That's the. Once that remark is made, then you can state theorems and even prove them if you have sufficient technical capability. But they sat down and did it. It's a IHS volume. Okay. So how does one notice that B, if you take the V as the V0 as highest weight vector, sorry, V0 in V lambda rho, then you also have the fact that if you take H in T, H or TC, which is what I called B, this would be TC. I mean, since I'm all the time working complex, these are the should be TC. H of course is inside there. For H in TC, you have rho H on V naught is lambda rho H times. It's an eigenvector for H with lambda rho is weight. So the entire one-dimensional surface C V0 is stable under rho B. In fact, what happens is this: we also have rho of any element x in n plus applied to V naught 0 for every x. Because n plus sum of these spaces all correspond to positive roots. Any one positive root applied to V naught is 0 because it's the dominant. So lambda is the highest weight. N plus annihilates. We have seen that rho G alpha V naught is 0 for every alpha and phi plus. And the space N plus is spanned by the positive G alphas. So every one of those G alphas annihilates, and therefore any sum of vectors coming from that also annihilates V naught. So C V naught is entirely stable under rho V. Now let's look at V rho. Treat V rho. I call it V rho or V, or what did I call it? I don't seem to call it V. V is a module over the enveloping algebra UG. I simply call it U of the linear algebra G. I suppose you're all familiar with the notion of the enveloping algebra. Even if you're not, I'm not going to go into the definition of it. V is a module of the enveloping algebra. So this is a huge ring, and you can give a map of UGC or U into V as follows. Namely, let me keep row there, V row as follows. Take any element X in U, map it into X V. This is a U module, left U module homomorphism. Morphism. And it's clear that the elements sigma n plus, sigma, what I call n plus, annihilates V. In other words, n plus is in the kernel of the span. N plus is the subalgebra of the algebra, and therefore a subspace of U, and it's hence let me call this map something. Let me call it pi. N plus annihilation, that is pi of n plus is in the kernel of map pi. Other and also H minus lambda rho H is in the kernel pi for every H in TC. This simply say, we are saying, this simply says that V is in the eigenspace corresponding to lambda rho for H. So these are all annihilators. So let I rho be the left ideal in U generated by H minus lambda rho H H in BC and n plus. It's easy to see that V rho is isomorphic as a modulo G or modulo UG to U by I rho. As a UG module. If V rho were irreducible, it would mean that V rho is simply U by I rho by this ideal. But we do not know if U by I rho is going to be irreducible or not. In fact, U by I rho is not irreducible. What is true is that U by I rho, this is called the Verma module. Corresponding to lambda rho. Actually, the definition of Verma module, you don't need a dominant linear form at all. Start with any linear form. You can look at the ideal in U. You can look at the ideal generated by H minus instead of lambda rho, any linear form, and n plus, and parts of the quotient. That module is called Verma module. One of our compatriots, and this was named after him by Dixmier in a book on relative representation which he wrote. So, D.N. Verma was at the Tata Institute. He's no more, but he was at Tata Institute for quite some time. Okay. I do not know if is there any object in representation named after an Indian working in India other than this. Okay, so what is true is the following, that Dharma lambda, I call it BD. One must spell his name with a E or a A. Is the, let me be the Burma module corresponding to lambda.
So this initial, sorry, initial D dot and
I'm not asking about the initials. Fortunately, display didn't use initials. It didn't go to the Burma modules. DNS Dayanand, by the way, is also proved by Parthasarathy Rangarao and Varadaraj. PRB. The PRB paper also is proved that what I'm going to say is proved. But it antedates that also. I mean, Burma modules were named late, but Burma, they were considered much earlier. You can see an extensive discussion of Burma modules in Sophistry Seminar, for instance, which dates back to 51, 52, something like that. Anyway, the theorem is the following. This Burma module, where lambda, for any lambda in TC star, no condition of dominance or integrality, nothing, any linear form, lambda in TC star. The Burma module lambda as a unique, irreducible quotient. Which let's call that V lambda, such that V lambda is isomorphic to V mu if and only if lambda. I don't know who this theorem is due to. I mean, it's proved in Sophistry Seminar. Though they don't call it Burma modules, it's proved there. It's equal to saying that the V lambda is, but the Burma module has a unique maximal submodule. Proper maximal submodule. It's a unique maximal proper submodule. It passes the quotient to get the unique. I'm not going to go to the proof of this. It's actually the proof of this is quite easy. It's a good exercise that there's a unique module. But the more interesting fact is this unique quotient V lambda. V lambda is finite dimensional if and only if lambda is dominant in time. This is essentially what gives the classification theorem. You start with the irreducible module. It has a highest weight, and therefore it becomes a quotient of V lambda, where lambda is the dominant weight. And so any finite dimensional irreducible representation is really obtained as a quotient of the Burma module, but the quotient is unique. The Burma module is unique, so you get a unique representation, irreducible representation with that dominant weight. And the rest of it follows from other statements. Say V lambda is small to V mu. It follows that if lambda even only if lambda equal to mu, I said, and then the corresponding unique maximum is in simple mode. So quotients are also going to be isomorphic. It's unique, the quotient. So that is the classification. That yields the classification of all irreducible finite dimensional representations. This is the crucial fact. The quotient is finite dimensional. In general, you get an infinite dimensional space, most lambda. But if the weight happens to be, if the lambda happens to be dominant in the integral, then you get a finite dimensional representation. If it's integral, it's not enough. Integral and non-dominant, you will get an infinite dimensional representation still. It has to be dominant in the integral, then you get a finite dimensional representation. So this is what essentially proves the classification. Okay, so I'm not going to go to the proof. The proof is not all that difficult, but there are some tricky points. So that's why I won't go to the proof, because I have only 5 more minutes, in which time, and obviously I cannot prove the theorem, but I'll give you some indication of how it's works. So proof of is the one proves is that by induction on the dominant weight. In the order on this time. As you suppose you have proved it for all representations with dominant weight less than or equal to lambda, then you want to less than lambda, then you want to prove the same thing for dominant weight with weight lambda. So that is the inductive step. And so what happens is this. So assume the formula true for these things. For assume formula holds for dominant mu less than lambda. Then you want to prove it for lambda. Now what one does here is the orthogonality relations between if you have representative functions of one irreducible representation and another, if they are inequivalent, the corresponding representative functions are going to be orthogonal to each other as functions on the group in L2 of G. That's, if not, even then, suppose you call the matrix coefficients in one representation rho ij, the other rho prime ij. If the same ij in the indices now, then the rho ij integrated against rho jk will be 0 if ij is not equal to jk. If ij is equal to jk, you get the internals 1. That's the kind of statement one gets. One has to make use of that. What one does is the following. First, note that the character chi of rho lambda will be something like sigma w lambda. Yeah, w lambda. See, you are going to, the average means what? You are going to take the eigenvalues, various eigenvalues, and add up. That's how you get the trace. So it's going to be the various eigenvalues contain, once lambda is an eigenvalue, w lambda is also an eigenvalue for any element of the wide group. Because w normalizes the torus, and if you apply w to the vector for which the corresponding eigenlinear form is lambda, if you do that, you get the new linear form is w lambda. So chi rho lambda, so once lambda appears, w lambda will also appear. If lambda appears with a certain multiplicity, w lambda will also appear with the same multiplicity. So, if that multiplicity is n lambda, so you then lambda W lambda is going to appear if lambda is highest weight. And as you go along, there are various other characters which appear, but if you fix any character, all its Weil group translates will appear. And you take the highest of those, that turns out to be dominant. That requires a little bit of proof, but it's true. So you take the highest of those. So what happens is this. So if you like, and if you look at the fact that, yeah, this is another thing that I have to say. The enveloping algebra can be written as u of n minus. N minus corresponds to all the negative roots, like what we did with n plus. U n minus times the enveloping algebra of Tc times u n plus. So when you apply it to V, u n plus kills the vector V, and when you apply it to V, you get the whole module. The n plus kills it, UH keeps that space into itself, so it's multiple of V, and then you are going to apply un minus. Each time you apply something from un minus, it goes the original lambda to lambda minus something. The whole thing, everything is there. So every character, eigencharacter in V rho is of the form lambda rho minus sigma m alpha with alpha and phi plus and m alpha integer. That's the way it looks. Everything lambda minus sigma m alpha, the integer greater than 0, m alpha greater than 0 integer. So every character in V rho is of this form. And if I fix one of them and take all the Weil group translates, you can get one which is dominant. So in each of them there is a dominant one. So I call the various dominant weights you get that way, I call them mu. So chi rho is going to be just this. I am simply adding up all the eigenvalues, which is how the with multiplicity. And use the multiplicity with which this particular character appears. So that's how it looks. Now, this is nothing but averaging over W. So this is an element we know it belongs to what I call T. It's a character is invariant under the Weil group. Oh, sorry, another 5 minutes. Then mu less than lambda. We know that chi mu is this expression sigma W mu rho, W mu dominant less than lambda rho. Then we know that this is W mu epsilon W divided by sigma epsilon W rho R W1. This is chi mu. Now I want to compute chi lambda. I know that chi lambda is necessarily of this kind, which is symmetric. Notice that each one of these is symmetric. And yeah, this lemma is not difficult to prove, but I will say this. If any symmetric element is a linear combination of elements of the form which appear sigma epsilon W mu divided by epsilon W R. Basically, it's you start with a symmetric form and multiply it by epsilon w wr. You end up in a alternate. One is symmetric, the other is alternating, so the product is alternating. And what every alternating thing can be obtained by average. If you have an alternating thing, average it, you get it back. When average it, you add up the sum and divide by the odd of the while group. To do that, you obviously get it back. So every anything is a linear combination of any function in FT is a linear combination of characters in any case. So if for each character you do that and then do it suitable number of characters, then you find it's proof that any symmetric form, say a symmetric function is necessarily ratio of two alternating functions. It's one small thing has to be brought into account, that this quotient is not obvious as a regular function. That is true. It's usually proved by using L'Hopital's theorem. The problem only arises at places where one of the denominator vanishes. And at those places you apply L'Hopital and differentiate and you get what you want. So, this is, use this lemma. So, as I said, you take the character, multiply it. Take the character and multiply it by this, or rather, divide it by this, then it becomes a symmetric. Which way I was saying it? Yeah. Divide it, then it becomes an alternating thing. And if it's an alternating thing, it's going to be something like this. But the induction hypothesis, if you look at these things, other than this, they all will come from the earlier dominant phase. And therefore, this is the only new thing that figures. And to get the equality, you have to apply the orthogonality relations. The new one can only be the sum of elements of this form, which includes the 1 by 1 plus others of lower things. And if you look at the characters of lowest things, there will be alternating forms involving only lower things. I'm not saying it too well. Use the orthogonality relations and then you get the theorem. Sorry.
The entire integration formula has to be invoked.
The point is to invoke, the reason you have to invoke from this, you are doing integration on G, but then you would like to, for class functions, want to convert integration on G to integration on T, because the function is determined on T after all. So what you do is look at the map, G cross T, G, which factors through G by T cross T to G. Put back the hard measure here. What happens? It becomes the invariant measure here times a certain measure here. And this measure turns out to be absolutely continuous with respect to the hard measure, and its Redondo-Nikodym derivative is nothing but if I call this delta, it is delta and delta. That is the Redondo-Nikodym derivative. So it amounts to integrating the character, the same thing as integrating this function multiplied by delta. Use that fact. So for the orthogonality relations, for instance, it amounts saying to take chi rho t and chi sigma t for two different rho sigma, and then to integrate on the torus, integrate the original thing is integrating this times the bar of the other character times delta bar here, which will cancel out. That's no, I'm running out of time. I really shouldn't take more time. I'll stop here. Thank you for